Hello everyone, my name is Niamh PAMMENT and I'm a second year environmental engineering degree apprentice. When a lot of people think about environmental engineering, they think a lot about solar panels and renewable energy. But today I'm here to talk to you about the effects of climate in terms of environmental engineering. So environmental engineering to me is about understanding, defining and simulating the real world environment in which our products are exposed to. So in a real world term is really high and really cold temperatures, and we simulate that in climate chambers. So instead of doing renewables, it's how the climate affects our products and affects cargo. So in real world environmental conditions are complex, but they're also predictable. We can simulate these environments by breaking them up into different elements that can be represented in a lab. This allows us to test our products inside real world conditions inside a laboratory. And this is, I find, really interesting because a lot of the time you don't get to see like the effects of the harsh climates, but I get to see it in my day-to-day job. So environmental conditions have effect on products. This can occur naturally or due to external factors, and this is what we call induced. So we can have temperature naturally and induced. So the temperature on a normal day, so 20 degrees if you're lucky, so you'd have that, but temperature can also be induced. So if there's a lot of friction on cargo, it can get really, really hot, or if you're in a cargo bay where there's fuel dump, that can also be really hot. Humidity, you've got the natural humidity of Earth as well as humidity in certain climates, and pressure change is the same. So in every day you'll have pressure change, but if you're in a plane and the plane goes up, there's definitely an increase in pressure. So we can simulate that. So natural weather will also have a toll on cargo. So, for example, rain, hail, and snow can be really harsh climates that our products have to endure. As well as this, they have to endure solar radiation. So, you know, when you leave plastic out and it's white and you put it in the window and it turns really yellow, solar radiation can cause brittle effects. We also ice can get inside products and then it expands, and then when it melts, you can get water going in your products, and that's bad if you've got electronic circuits. So how do you battle that? And also wind can be a major issue, because it can blow dust into our cargo and our products, which can cause foreign object debris. So from the induced side, shock and vibration, if you accidentally drop cargo on the floor, is that going to survive? Um, Corrosion as well. So certain metals, if they react to things, they can corrode, and that can create weakness in cargo. And acceleration. So if it's on the back of a lorry and it's traveling fast, will it be able to survive that? In real world, many of these environments exist at the same time. So example, if your products are in a jet air carriage, there's really, really high vibration levels due to it being near the engine, traveling up into the air. There's lots of low pressure up there. It's also extremely, extremely cold. You also get exposed to rain, shock, snow, hail, and then you also get landing shocks. And how do we simulate that to make sure it doesn't affect our products? So a ship is a really complicated one because you've also got to include having a salty atmosphere. You also see a lot of rain, snow, ice. You have low vibration levels but high launch shocks, hot and cold temperatures, and high humidity. And in a desert, you have a really, really hot climate. So you'll have really high solar radiation, sand and dust, vibration and shock behind a vehicle, and rain, sun, and humidity. A shaker system versus a loudspeaker. So in a day-to-day, in principle, the shaker operates like a loudspeaker. The voice coil of a loudspeaker pushes and pulls a cone in and out, causing sound pressure waves. In a shaker, it is the armature core that moves in and out, causing vibration. So we can explain this with very basic physics. So an electromagnetic. Most people know what electromagnetism is. When electricity is passed through an electric current in a coil, a magnetic field is produced around it. An armature force in a shaker is directly proportional to the current in a coil. So this can be simulated by the left-hand rule, so you can figure out which direction a magnetic field will travel into. So if you consider the speaker again, when waves of electric signal from music device such as a CD player amplified to the speaker voice coil, the voice coil turns into an electromagnet. A north and south pole is created which attracts or repels from the permanent magnet. When the electrical current flows through the voice coil, it changes direction, causing the coil polar orientation to reverse. So the constant change in polar orientation will cause that vibration, and in a speaker that creates sound, but in an armature it creates vibration. So an electrodynamic shaker armature coil. So if we compare that to your speaker, an armature coil responds in the same way. In a small shaker, there is a permanent magnet. This magnet attracts and repels the magnetic field of the coil, causing movement by pushing or pulling. The size of an armature affects the frequency range in a similar way to a large loudspeaker, limiting low bass frequencies. So as you can see in the bottom picture, we have the center pole, which can be a permanent magnet, and the different complex systems inside that to create that electromagnet. So how does that relate to real world environments? So we simulate sine and random vibration. So sine vibration is based on a sine wave, and you can program that into the shaker system. So this simulates cargo being in the air, so where it's like you see very predictable waves of vibration, so it's less intense on cargo. But when you put random vibration in, it goes up and down and it's really intense and it can do a lot of damage. And this can be in a real life situation if you have it on the back of a lorry and you're going down a really, really bumpy road. So we try and simulate that as best as we can to figure out how long the product would last under those conditions. So as an environmental apprentice, I don't just do shaker systems. So my day-to-day is I set up fixtures for climate chambers and shaker systems. So I do a lot of stuff with ham rigging, so putting the cargo on top of the shakers, making sure it's all bolted incorrectly in towards our fixtures. And it can be a really complicated job if you have a lot of fixtures and you need it in set positions. So with that, I use overhead or hand cranes, and I have to do certain electrical overhead crane training to be able to use these cranes, because often you're carrying really, really heavy tons. So for like health and safety reasons, but it's really interesting to learn how tying rigging in different ways will affect how much you can hold. So I also do the programming of the chambers, and I collect the results from data loggers. So we'll often have a climate chamber that will cycle and it will go up to plus 74 and minus 20. And we'll log everything on a data logger, and then we'll take that data and put it on a graph to show that we have met all the climates that we hope to achieve. And we'll have a section of error, so above or below, to make sure that if we don't go over those, otherwise our test becomes invalid. I also do internal calibration. So I do a lot of internal calibration with bungee ropes that we use when we do some of our rigging. I'll also do internal calibration of modal hammers. And we do this every year to make sure our equipment is reading what we should be, especially with bungee ropes, because if you overstretch them, they, like a hair tie, when they become brittle and they pull, and that means that they're giving us bad readings and we can't use them anymore. So internal calibration is really important from that engineering point of view. I also write test programs. So a lot of the internal calibration I've been doing, writing the test programs for that. And when I lease off my apprenticeship scheme, I'll be writing real test programs for our cargo. I also am lucky enough to have access to a high speed camera at work. And this is to film different shutter speeds, and this is something that's really interesting and kind of a forefront of technology at the moment. I also, as I said before, use the electrical and overhead cranes. And what I love about my job, it is absolutely different every day. And then I think there's a lot more to environmental engineering than just climate change, and to see how the everyday climate relates to a real life cargo. But obviously, as climate change changes, my job and my specs I'll have to go to is different. So it definitely links in. But thank you guys for listening. Any questions?
We do have a call on the call. So we'll just give it a few minutes to see if any questions have arisen. So did you always know that this is what you wanted to do when you were at school? Did you know that you wanted to be an engineer?
Actually, no, not entirely. So at GCSE, I did do a BTEC in engineering, and I quite enjoyed it. But when I picked my A levels, I picked maths, physics, and art and design because I was looking to going to architecture. And then in the first year of A levels, I realised that doing that art and designing bit wasn't for me, and I wanted to do something practical and more hands-on. But I've always enjoyed doing maths. I've definitely preferred that in my entire life. But I think engineering really appealed to me at A level, so I don't think it's ever too late to consider engineering as a degree or as a career.
Great. Okay, doesn't seem to be any questions.
Okay.
So I think what we'll do is I'll stop the recording.